Welcome to Calculus. You're at the beginning of a rather long journey that I hope will be as much fun for you as it was for me and as it still is for me. But before we get started, we may want to answer possibly the most important question about the whole thing, and that is, why calculus? Why are you in this class? Why do you need calculus? Well, let's take a look. So why do I need calculus? An answer that could very well be given is very, very simple, and that is, it's a required course. And so welcome to my admittedly rather dry sense of humor, but even if we don't want to joke around, that may well be the answer right now. When I started taking calculus, it was simply the next course in the curriculum. It was math, so it ought to be fun. That was about it. But now, let's dig a little bit deeper, and let's just assume that the people who set up the requirement knew what they were doing. I'm pretty sure they were. And then the next answer is that calculus certainly is fundamental to science and engineering. Calculus opens the door to plenty of applications, and calculus also trains your brain to a new level of accuracy and analytical ability. And the reason why I have more slides than just this one is because for the rest of this presentation, I want to talk you through these things in a little bit more detail, show you some of the cool pictures, and also then talk about what you can or need to do to make sure that this becomes a good experience. So, why is calculus fundamental? Well, algebra alone is not good enough, or is not enough, simply, to analyze quantities that vary in time, such as velocities. That's one of the fundamental first things that we will talk about in calculus, and it will stay with us. Algebra alone is not enough to compute tangent lines. That alludes to the geometric aspect of calculus. Algebra alone is not enough to find turnaround points of graphs, which is somewhat surprising because when you look at a graph, well, you just find the turnaround points visually, right? And algebra alone is not enough to compute complicated areas, such as the area under a parabola. And algebra alone, and here's where it gets really interesting also, algebra alone is not enough to solve complicated equations, because many of the complicated equations that arise in science and engineering, which are algebraic equations even, need calculus-based methods to be solved approximately. Okay, now all of this is stuff that also certainly talks about pictures, and so we will also take a look at the pictures in just a little bit. It took over 1600 years from the ancient Greeks, or from these ancient Greek philosophers that mathematicians certainly are still rightly very fond of referring to the discovery of calculus. And so that means when things get a little rough here and there, don't get discouraged. This is something where we have to jump over a couple of mental hurdles, certainly, and those are not hurdles that are just set up because people want you to jump a high hurdle. We are really facing the way reality or the way mathematics is, and so we just have to handle it as it comes, and we will. So, what are applications that become accessible through calculus? Well, there are those aforementioned tangent lines. So in this animation here, the blue line is the tangent line. The red graph is a parabola. It looks like a parabola, and it really is. That's what I used to make the animation. And the way you define a tangent line is, well, it's supposed to fit the graph smoothly, right? That's what people always talk about. But what you need actually to really compute the tangent line is this technique from calculus that is visualized here, which is that you compute secant lines, which are lines that go through these 2 points, the red one and the pink one, or purple one. And as those 2 points that you use to compute the secant lines get closer and closer to each other, you can also see here that the black secant line starts tilting towards the blue line, which is the tangent line. And so that is where calculus becomes a process. That is where calculus becomes a movie. That is where algebra alone doesn't do it anymore, because all of a sudden we are no longer looking at a single equation. Areas under curves become accessible through calculus, because if I want to compute the area underneath this parabola here, there is no formula that you can look up in any formula collection that I know of. And there shouldn't be, because there are plenty of areas that are bounded by all sorts of strangely shaped curves, and it would take forever to set up the formula collection for those things. So again, calculus becomes a process, and the process is that you approximate the area with rectangles. And as you can see here, okay, these rectangles, the heights of these rectangles are always the value of the function at the right endpoint. And the more rectangles you use, the closer this blue area is to what the area under this red graph should be. And in the end, or as we will say in calculus, in the limit, the two areas are the same. Once we've got that, we can talk about things like shapes that make optimal use of resources, such as, for example, the shape of a soda can. The shape of a soda can is subject to many constraints, because these things must be stackable in certain ways, so that first of all, stuff doesn't slide off, so that cans don't slide off from each other, and they must resist a certain internal pressure, they must resist a certain downward pressure, and so on and so on. And at the same time, the way soda cans are designed, standard soda cans, standard 35 fluid ounce soda cans, 35 fluid ounce, 12 fluid ounce, 12 fluid ounce soda cans, the way those things are designed is with using the least amount of aluminum in mind, and that is something where then certainly there is a very happy marriage between conserving resources as well as the legitimate interest of industry to make a profit, because the less aluminum you use, the less we use of a precious resource on the planet, and at the same time, the less aluminum the manufacturer has to buy in order to make the can. By the way, this image is courtesy of a major US manufacturing company, as they request to be referred to, so this is real. And one of the things that you will find as we are working together, one of the things that you will find as you, I hope, will work with me, I will try to keep it as real between the two of us as possible. If there is a real application that is accessible from what you know, I will do my best to put that into the presentation, to put that into the class, so you can see it, because as I will tell you all the way through, calculus is real. We will need our imagination, we will need creativity to visualize the various things that happen in calculus, but calculus is not a figment of our imagination. It is real, and it has very, very real consequences. Something else I want to say here is that anytime I use an image that I have not created myself on my computer, I will give a proper attribution. As I do that, do not assume that the attribution means that my work is being endorsed by these companies or by these entities. That is plainly a legal thing, where people who give you the permission to use their work protect themselves from being held responsible for endorsing something that they don't fully know. Because the only way any of these companies and entities could endorse what I'm doing would be if they review the whole course, and yeah, that would be a little bit lengthy for someone who just gives me permission to use one image. Alright, so that's more of a legalistic thing, and I hope we don't have to worry about that at all. Let's get back to the fun stuff. Other things that we can do with calculus is we could compute, or at least figure out, how much energy it takes to get to an orbit of an object in space, such as, for example, the International Space Station. And there's another NASA image credit, and this image connects to a computation that we will do, which computes how much work it takes minimum, how much work it takes at the least to move a payload to orbit. And it turns out that the minimum is very, very small, but of course the challenge is that in order to get that minimum into orbit, you need a booster rocket, and again, this is another NASA image for which I am grateful. And well, that's where then the fun starts, that's where the engineering starts, that's where the physics starts, that's where the stuff starts that most likely you will be doing with calculus, so that's what you might be doing after you leave me in this course way behind, and I want you to do that, because I want you to be able to do things that I can't do. Other things, well, hey, cool stuff that I liked. I always liked complicated volumes and neat shapes like a torus or, for example, an ellipsoid. And these are volumes that we will compute. I think both of those are actually homework problems. And if you're wondering right now, oh my god, how am I ever going to get there? Look, you're working with me. I'll get you there. All right? Okay, what else do we have? We can talk about statistics. And one of the things that you may have already seen in a lab is that when you take measurements and you compute your experimental average and your standard error, then people talk about a 68% likelihood that the actual value is within one standard error of what you've measured, that there is a 95% likelihood that what you measure is within two standard errors of what you've measured, and there is a 99.9% likelihood that what the actual result is within three standard errors of what you've measured. Well, we will use statistics, calculus-based statistics, in order to explain where these facts come from. Other things, well, we can talk about vector fields, and here's a very simple image that I took myself with a colleague from physics, where we simply put a magnet underneath a piece of paper and we put iron shavings on top of that. It's a very standard thing that you can find on the web where people say, yes, this is something you can do. Do you think I ever actually found an image that I could just use? No, I didn't. And so I made this image with a colleague, and at some point in time, because I'm not terribly good as an experimentalist, I actually felt kind of bad that I was wasting this physicist's time. I mean, this was a guy who was working with accelerators and things like that. I mean, every piece of equipment that he needs in his experimental work costs a whole lot more than a little bit of iron shavings and a magnet. And so I was about to apologize to him when he looked over my shoulder and said, man, this is so cool. And that's, I hope, the enthusiasm that you'll take away from calculus and from science, because it is neat even if it's simple. And then, of course, the other thing is, one of the nice things that I'll try to do also is I will overlay the model over the reality. And that's, of course, the art that scientists and engineers ultimately also try to perfect, because the model is what we can control, the model is what we can compute. The picture doesn't need to be the same as what we actually have in reality, because you can see the field lines of the magnet actually bulge out a whole lot more than the field lines in this picture, but we get a decent representation of what's going on, and then we start working with that, right? And so vector fields are something that we will also be talking about. And ultimately, that actually, through partial differential equations, leads to quantum mechanics. And this was one of those pictures that, when I made it for my differential equations course and differential equations book, which you can also take with me, that was one of the things that pulled a lot of stuff together for me, because this image you may have already seen in chemistry class. That's an image that people often associate with the d orbital of an electron in a hydrogen atom, if we want to be completely precise. And that comes out of solving some really, really hefty partial differential equations. It comes out of solving the Schrödinger equation, which is a computation that is nasty, and it is a computation that you can go through with me in the differential equations class. If you stay on the regular pace, it'll be about 2 years from now. And it's hard. Well, look, I told you I want to keep it real. I can't invent a better and simpler hydrogen atom. Or let's just say, if I could do that, I would take my Nobel Prize and, who knows, solve the world's energy problems or something like that. Like I said, I have to keep it real, and sometimes that means we have to work really hard too. All right. The other thing that happens is that calculus trains your brain. And so how does it do that? Well, you will solve problems that are longer and more involved. And that means you will learn to concentrate better and for longer periods of time. This is sort of like when a cross-country team starts preparing for the next season. The first few workouts are just rough because people are out of shape, or at least not as well in shape as they need to be for the grueling and very rigorous demands of a competitive cross-country season. But it gets better, because as you practice, you will get stronger. Problems will require that you recall facts that you have learned in algebra, geometry, and trigonometry. So you will learn to reactivate dormant memory, or you will learn to review until it is no longer dormant. There are all sorts of things where I will simply have to trust you to, when, hopefully if, you can't remember something, that you look it up. Mathematics is very much unique in that it builds and it builds and it builds, and I've done it for 20 years at deeper and deeper levels, and there are still things that build on top of everything I know that I don't know. So we're looking at something here that is very, very beautiful. And so when I tell you these war stories about myself, that's not look at me, ho, hey, great for me, and all these things. I still, after 20 years, still stand in awe of this construction that is modern day mathematics. And there are still plenty of situations where I'm a student and where I potentially cry the same hot tears that you cry. It's just, for me, it's in differential geometry or in quantum mechanics by now, at levels that when I was your age, I couldn't really fathom yet, and there's nothing wrong with that. We work until we get there. Problems will require visualization, and that may well be the biggest challenge, and we'll talk about that again when I tell you a little bit about how single variable calculus and multivariable calculus relate. Because what you need to do is you need to see pictures in your brain. And I'll show you plenty of the pictures that I see, and I'll show you plenty of the stuff of the movies that I see in my brain. But nobody knows how to put those pictures into your brain, and only you yourself can do it. What we can do is, we can show you plenty of those things, and I will do that, but beyond that, anything else, when people say visualize, when people say think real hard, all I can say is, yes, honest to goodness, I see those pictures, and I hope by showing you the pictures I see, you will be able to create your own pictures. So, let's think about some facts about the brain. And that goes in the direction of what you need to do and what you can do. One of the things that quantitative psychologists have found out is that every human being has about 7 memory slots that allow us to keep track of things. And so that means for more complicated tasks, our brain will start segmenting information. For example, when we talk about phone numbers, those things are 10 digits long if the area code is included, which means if these were 7 very mechanical memory slots, it would be impossible to memorize 10 digits. And so what happens is that typically these things are memorized as groups 3 plus 3 plus 4 or similar, and not as individual digits. And that means you need to learn how to segment information, and insufficient segmenting of the information can lead to this phenomenon of not seeing the forest for the trees, of calculus being amazingly hard because you are stuck in the details. And what we need to do is we need to make sure that we don't get stuck into those details, and that may sometimes mean just a lot of practice with computations. So when something is confusing, typically the information is not processed appropriately or is not processed in a way that unconfuses it for us. And so we'll need to find a way for you to adequately process this information. There are certain standard ways that I can talk about, but in the end it's again something that very much depends on the individual. So, for example, in terms of segmenting information, the most important first step is to be secure in your algebra and trigonometry. The less conscious effort you need for these fundamentals, the easier the harder parts of calculus will be. So spending little conscious effort on something does not mean, however, that we try to sleepwalk through it. We basically need the type of familiarity that lets us recall that 3 times 7 is 21 without being terribly bothered by it. And so, yeah, no, we don't use calculators for simple complications there either. So similarly, we need to internalize the methods of single variable calculus so we can execute them smoothly and with as little conscious effort as possible. I literally mean this complicated stuff, if this can become to us, as second nature as 3 times 7 is 21, then we will be in very good shape to go deeper and deeper and deeper. Now, if algebra was not such a good experience for you, and I mean you're starting this maybe after a summer of taking time off from math after high school, and certain things from trigonometry and algebra you might not recall right away, well, there's a flip side to that also, and that is as you use algebra and trigonometry in calculus, you relearn it, and it also sinks deeper into your memory. And so there is a bit of a cycle going on. The more you are using your algebra and trigonometry, the more familiar you will also get with it here. And so this ultimately will make multivariable calculus easier, but also going into and through multivariable calculus will reinforce your single variable calculus. And yeah, truth in advertisement, like I said, I always want to keep it real. When I say easier, I don't necessarily mean easy. Easier just means it's not going to be a huge mountain that we don't know how to overcome anymore. It'll still be a mountain. Other things about the brain, we can concentrate on single complicated tasks. So for example, we can write detailed literature analysis. We can also multitask. For example, we can take a phone call while we're fixing dinner. But we can't do multiple complicated tasks at the same time. Whenever people exhort the value of multitasking, tune them out. That sounds very disrespectful to these people, but what I'm looking at here is I've reviewed a couple of just articles where people have really done quantitative brain research. And what turns out to be the case is that even though you think you can, you may not realize that your brain tuned out the music that you were listening to while you wrote that literature analysis. So even though you may have done two complicated tasks, like listening to an intricate piece of music, and intricate music, of course, classical music is right there, but there's also some pop music that is pretty intricate, and that's more likely what you're listening to, or whatever it is called these days. And literature analysis, of course, is also intricate, but what happens is that your brain will focus on one, not the other. And let's not get into what your subconscious does quite yet, because that goes, as far as I can see, also beyond what quantitative psychology can analyze right now. Or, and that's the other thing, and don't be insulted by it, you may have never faced a truly complicated and absorbing task. And that can very well be, because some people are bright enough that it doesn't bother them to do algebra and a couple of other things at the same time. However, first of all, don't take that as an insult. There's a lot of stuff that you have not seen yet. Trust me, because I have seen it. And if that bothers you, look, the harder you work, the more of it you will see in your lifetime. And let me be quite honest with you. It does bother me that there are things I haven't seen yet. And so I just keep working at it to see more of this fascinating stuff. And so, the best advice I can give you, even though it sounds horribly traditional and all sorts of other things, make sure you have as few distractions as possible when you study. If music helps you, so be it. But remember, most likely, you'll put on a playlist, and once you get absorbed by whatever you're doing, if it's calculus, if it's physics, if it's literature analysis, whatever else, you're not going to remember the songs that you've listened to. If you remember them, you're either a whole lot brighter than I can fathom, or you haven't really focused on what you were doing. But avoid interruptions. Turn off that cell phone, stay away from email or whatever people call it these days. I mean, Facebook right now is really big. And Facebook, it's a social platform, but in the end, it's just another way to communicate. So it's a fancy email to me, at least. And of course, I'm a little bit of an old guy here. And if you've got a rather social roommate, study in the library. Calculator dependence turns out to be a distraction too. If you've got to interrupt a train of thought to use a calculator to check a computation, or if I have to do that, then I/you must refocus after we put that calculator away, and that's not good. Because if that happens too often, the big picture does get lost. Believe me, I've gone through complicated computation where I had to interrupt, and where the big picture did get lost. And the only thing I could do was go through it again. So, quick thing here, that's not a fact of the brain, but also a quick, again, truth in advertising. I don't think calculators are the devil's work. I do use calculators and computers, but I use them for things that I can't do in my head. Okay, I use them for computations that are so big it isn't even funny. Using machines for tasks that can and should be done by people is counterproductive, and it can even be hazardous to your health. When I made those slides, was a while ago, but it's certainly still something that goes through the news. People always talk about the fact that many people don't exercise enough and drive too much. As a consequence, they're in poor health. Well, similarly to exercise being the solution above, to being the solution here, some people now use brain train software to keep their brain in shape, or in some case reactivate it. I've looked at that when some of that made the news, and it's good stuff. But a lot of the brain train software that people give to, in the worst case, Alzheimer's patients who just desperately try to hang on to who they are, when I looked at that software, one of the samples I saw was just mental arithmetic. And, well, just as people who stay physically active will not need to worry about the health consequences of being a couch potato, it turns out that people who stay mentally active won't need that brain train stuff because they will keep their brain with them. Mathematicians stay mentally amazingly acute to really, really old ages. Similar theoretical physicists. Similar to composers who do music all their lives. The danger that these people have to face is not deterioration from underuse. The only thing that we have to worry about are strokes and things like that, and that is much more of a physiological thing. Okay. Other things about the brain, again, there are quantitative studies out there that show that content is best learned if it's connected to prior knowledge. And we'll try to connect to physics, geometry, algebra, etc., to things that hopefully you have seen before. However, if something is entirely new to you, it probably will lay the foundation for stuff that you will learn later. That is what makes mathematics often such a hard sell, because a lot of times the content within which you will need the mathematics isn't quite there yet. However, let's keep in mind that if we always only stayed in that comfortable realm of connecting to things that we already know, there would be little or no progress, because ultimately we would just stay in that comfortable setting where we know everything, and as soon as we do that, there is no progress. So we've got to push in uncomfortable directions, in directions that we haven't seen before. Another thing where people have quantitative studies is that if you have to acquire content through hard work, then that content is retained better than content that was acquired easily. And that was proved through studies in which content was taught in an optimal fashion, as well as in a fashion where artificial intelligence, that's another story, by the way, and it's cool stuff, but artificial challenges were built in. Well, and so basically those were classes that were taught by someone who was distracted, or where you had multiple restarts, interruptions, things like that. Look, that on one hand means that even the most frustrating learning experiences can have an upset. And on the other hand, we're not going to make calculus artificially more difficult than it already is. There's no need for that. Calculus is already hard enough as is. However, if you stick with me, if you take the class with me, if you use my book, you will face exercises that go deeper and deeper and deeper until we hit your individual limit. Now, these limitations are different for any individual, and we shouldn't be bothered by that. I can't run as fast as an Olympic 5,000 meter champion. That's unfortunate, because I would have loved to be an Olympic 5,000 meter champion, but I'm not going to lose sleep over that. And so if you're not going as deep as some of your classmates, hey, work at your limit and push, and hopefully, ultimately, your limit will be their limit too. And so on the bright side, if something comes naturally, go with it. Hey, there's no shame in that either. But if, and actually when you hit what I call that wall, and that is something I've talked to a lot of bright people at transition points, algebra to calculus, single variable calculus to multivariable calculus, calculus type mathematics to proofs, where you have to change the way you think about things, and they all say the same thing in some way, they hit a wall. Things don't work the way they used to. Things are no longer as natural as they used to be. When, hopefully if, but most likely when, you hit a wall, remember this slide and then be ready for one of the most intense experiences of your life. Because that's where things literally change in the way your brain approaches content. It's frustrating. It's tough. If you just want to come to my office and just need to blow off steam, do it. Believe me, I've been in that very situation. And if my mother hadn't been with me during those dark hours, I'm not sure I would have made it through my curriculum. And I'm not ashamed to admit that either. I mean, those were hot tears that I cried. And hey, it's the cost of doing business. It's unfortunately part of pushing yourself to become stronger and stronger. And so now let's talk about some of the fun stuff again, because single variable calculus ultimately is but a first stage. Some applications of single variable calculus, like tangent lines and areas, are really neat, and we've already seen them, right? But they feel like mathematics for mathematics' sake, and that's in some way they are because they are. There's nothing wrong with that, but we want to use mathematics for something. Other applications like one-dimensional velocities are real, or at least they would be if the world would be one-dimensional. But our world has at least 4 dimensions, 3 space dimensions and 1 time dimension, and of course now there are fascinating theories out there that talks about hidden dimensions, which I don't understand, hopefully don't understand yet. That's another one of those mountains that I'm working on right now. And so therefore, optimization of shapes of soda cans notwithstanding, when it comes to applications, single variable calculus mainly prepares us for multivariable calculus, which ultimately leads to these vector fields, which ultimately leads to the Schrödinger equation, to those d orbitals and things like that. And of course that jump now needs us to internalize the calculation from single variable calculus. They need to be at the level at which we remember algebra. Ultimately, single variable calculus problems become parts of much longer problems, just like algebraic simplifications are about to become part of calculus for you. You need to structure your work. Problems will get so long that sloppy work will not just slow you down, they will literally be the end of it. I know of one case that I'm very, very unhappy about, where I told a potentially very bright young man that he needs to structure his work. I couldn't get it across to him, and it did lead to disaster because he made it through single variable calculus. He never made the transition to multivariable calculus. So when your teacher says, look, you've got to line things up, you've got to be able to follow these things, you've got to follow all sorts of what ultimately is like mathematical grammar, and how much fun is English grammar for that matter, it is necessary. You want to practice visualization and modeling whenever possible, because higher dimensional visualizations and models will be even trickier. And here's where we're hitting the fun stuff. Because the one-dimensional slices of a graph, so for example, if I tell you that if I slice a graph of a function in 3-dimensional space with vertical planes, and these are the slices that I get, and now it rotates around again, so you get something that looks like a bell curve. The bell curve gets higher and tighter, and then it goes back up, back down. Well, that sort of looks like a shark fin sticking out of the water. And if you look at the corresponding 3-dimensional image, you see that these 1-dimensional slices line up in space. I can connect them in the other dimension. And what you get as a picture is this shark fin looking thing, right? That's something that if we stay on track, if we stay at the regular pace, if you're faster, hey, good for you, but don't sacrifice speed and don't sacrifice accuracy and depth for speed. We'll see that about a year from now. This is something where you take 1-dimensional images and you put them together to turn them into 3-dimensional images. The tangent lines in 1 dimension, which you can also make slide along the graph, right? And of course that's just cool stuff that I like to see, but it's also stuff that I see in my mind. Those 1-dimensional slices are fundamental in multiple dimensions, because those partial differential equations I've told you about that we need to compute the d orbital and things like that require us to work with partial derivatives. And partial derivatives means you take your surface, slice it with a plane, and then look at the intersection, and then the tangent slides along. So you cut it with a plane, you focus on the intersection of 1-dimensional object, and that 1-dimensional object, for that 1-dimensional object, you use single variable calculus, because this picture now is basically the same as what you saw in the previous panel. Area computations, where we compute areas under curves, another animation that you have seen before. These things ultimately become the computation of volumes and more complicated stuff. So integration in 2 variables ultimately computes volume, where we can see the rectangles are replaced by boxes, and the boxes ultimately sort of look like that shape here, and that's the volume we want to compute, right? And so I got it stopped just in time, and it's now the same story, right? In single variable calculus, we added the volumes of areas. In multivariable calculus, we add the volumes of these boxes, and the net volume of these boxes, just visually we can see, that ought to be very similar, and in fact, it is very close to the actual volume. And so basically, this is something that ultimately leads to computations of things like centers of mass, centers of gravity, the way rotating bodies act, and so on and so on. And those are actually fairly direct computations and very direct connections that are not several steps into the future like the Schrödinger equation would be, for example. Those long computations, and if you want to, and you want to work your way through this here, okay, just hit the pause button and follow the computation. We'll see it in multivariable calculus. This is the intersection of a plane, and the plane is z equals mx plus 1 with a cone z squared equals x squared plus y squared. Well, that computation, even though we have to do the computation at an algebraic level and other computations at a calculus level, these computations are a lot easier to digest when we can also see what's going on. And what's going on in this calculation is that we've got a plane that tilts, and as this plane tilts, this red intersection turns from a circle to an ellipse to a parabola to a hyperbola. Let's take a look at that again. We start with a circle, but as the plane tilts, the circle stretches in one direction, becomes an ellipse, opens up to be a hyperbola, and a parabola, and ultimately a hyperbola. Okay, I've promised you, and I will keep telling you, truth in advertising. Okay, this is a cool animation. On one hand, it really is a picture that I saw in my mind, and until I had all the tools available for these animations, I could never show that to students. And that's also what people often see in class when the math guy or the physics guy stands in front and just does all sorts of shadow boxing where, and people have also told me that from lectures that they've attended, they saw the picture, professor saw the picture, they didn't. Okay, I hope we can avoid that here. But the other reason why I've put this thing right into this first presentation, which, if you will, is also an advertisement, is because it's cool. Look, I want you to get infected with that very same bug that I have here because, well, I want you to do this with me. And so, yes, what you have just seen was, on one hand, an exposure to a whole lot of cool calculus, but it's also an advertisement because with me, you're going to see that, and that's why I want you to stay with me. All right. Back to what's good for you, back to what's ahead of us, some final words. There are some advantages to using online presentations to learn calculus. One advantage is that these presentations are faster than class. My personal compression factor is about 2 to 1, or faster, which means the net number of minutes in the presentations for calculus is about half what I spend in a regular class. So if you can pick up everything you need here, you'll save time, and that's not wrong, not bad. And if parts are too fast, you can rewind in places where you, specifically you, not someone else who asked the question, but you need to be careful. And that is something, even though in lectures you can ask questions, let's be realistic, most people are very uncomfortable with that, and so questions go unasked. Well, here you can simply rewind. Nobody knows if you have to rewind something 5 times because it's just between you and I won't tell because, well, I can't tell because I don't know how long you rewind me. Disadvantages of using online presentations? Well, again, welcome back to my sense of humor because one of the disadvantages is that they are faster than class. And that means you don't want to simply speed through those for the sake of impressing yourself. Calculus is best learned by being methodical and consequently by being a bit slower at times. I've taught this class in a flipped format where students are required to watch the presentations and then come to class and we work on deeper problems, we answer questions that may have come up, we work out some truly nasty stuff. But what I have found is some of the most successful students in that class have a set of notes from these presentations that look as if they attended class. And so Don't even forsake things that sound rather old school, such as note-taking. The act of writing key information down uses different faculties of your mind to hardwire the information in your mind, and therefore these other avenues will also make the content sink in deeper. So you can't ask questions when all you have is the recording. Yeah, that is a disadvantage. So if you watch the presentations as part of a class, online or face-to-face or flipped format or whatever else, we will find in the next, hopefully, couple of decades that I'll still be around in this business and in this world, ask questions in office hours. So my suggested approach for using online presentations to learn calculus are work the discovery activity if available. And in my book, there certainly are discovery activities for quite a few of the sections of the modules. Then you want to read the section. Then you want to try the practice problems on the activity if that is available, or start some homework problems. Then watch the presentation. So everything is geared here towards you facing the content, working with it, working hard with it, potentially working through some of your problems already on your own, and then solidifying it. Of course, if you get stuck at some point in time, definitely watch the presentation. Then finish the practice problems, then do the homework. So the more you can do here by reading the text, the easier technical classes will be, because no matter how much progress we have made, no matter how many animations I can show you, ultimately, whether it's the web or anything else, the primary mode of dissemination of information will remain written words. And so you want to be able to read a technical text and see the pictures in your mind. Because ultimately, I can also tell you that, we'll always keep it real between us, it takes a long time to make these animations. And so ultimately, you will read texts that are written by people who are much more regarded in their fields than I will ever be in any of the fields in which I am doing research. And those people will be, because it will be so deep, will also struggling themselves to simply make it intelligible, and they simply don't have the time to also make animations on all sorts of things, and there may not even be animations, because how do you visualize 11 dimensions? I do not know. So train yourself as much as possible. The harder you can work through here, the more of a payback you will have. Seek help as needed. Of course, if you bang your head against the same wall for hour after hour after hour, look, you need to ask questions. Stop by with me. And so that's the office hours. Although, look, I may have been a bit preachy about going through various things about what you have to do and how you have to adjust. And although it's very likely that some adjustments really will be necessary, and although parts of calculus will be hard, and although there may be other things that will bother you in calculus, enjoy it. Don't be scared of it. Nothing of what I've said here is meant to scare you away. I just want you to get ready. Discovering calculus was still one of the singularly most impressive human achievements that happened in, if I got my English vocabulary correctly, happened in the 17th century, and the names associated with it are Newton and Leibniz. Calculus is the gateway to truly fascinating science. Okay, if I haven't gotten that point across, you either have to watch this presentation again, or maybe I'm just not the guy to talk to for you. And that sense of achievement and the high relevance of calculus will make it really well worth the effort. Okay, we're at the end of this presentation. And once again, I've done something that often also happens when I substitute for a colleague. I walk in, I talk about math, we have a great time, it's all fun, hopefully it was. And at the end of the class, some student just raises his or her hand and says, "Who are you?" Well, yeah, I literally have walked into 75-minute classes. People didn't know who I was. Sometimes they didn't even know that they had a substitute. I just hit the math. Look, if you want to know who I am, name and affiliation are at the bottom of the slides. You can Google me, you can look at my Vita and everything. The short story is very simple. I'm the guy who teaches you calculus. We start with limits. I'll see you there. Whoop.